Hello and welcome back to TWSS2022. My name is Colleen. I am the sales coordinator here at TechX. Thank you so much for joining us today as we are on our third presentation for today. It's almost our last one. We do have one tonight at 7 p.m., but that is a repeat of the one we had this morning. With me today is Dr. Tom Jenkins, who is going to be talking to us about using VSim, as you can see, to model low temperature gas discharges. Dr. Jenkins is a senior research scientist here at TechX. He specializes in the theory and computational modeling of RF and magnetohydrodynamic phenomena in plasmas. He is a developer for the VSim code, a past developer of the Nimron code, and an experienced user of high-performance computing platforms at OLCF and NERSC. Throughout the past several years, he's worked collaboratively with members of the RF SIDAC team to model nonlinear wave phenomena, impurity reduction, and sheath physics associated with RF antennas. In addition, he has published research on various noise reducing and speed limiting algorithms for faster and more accurate nonlinear plasma particle and cell modeling. So welcome, Tom. How are you?
Doing well, thank you.
All right, I will leave and pass it on to you.
All right, and you can hear me and you can see my screen, I presume, at this point?
Yep, everything looks good.
All right. Okay, so I will be talking today about our work to model low temperature plasma discharges with VSim. I want to thank collaborators on the VSim and the VSim examples and composer teams, and a couple of folks up the hill at CU Boulder as well in the Center for Integrated Plasma Studies. We'll be talking about some work we've published together in this context. And just overall things I want to go over in this talk, I'll be talking about Townsend discharge physics and one of our new examples and our parameter scan feature, which you've probably heard about previously in some of the talks, but it's a good feature, so it's worth mentioning again. I'll be talking also about neutral gas breakdown and computing Paschen curves using VSim, which is our recent publication with CU. Some words about the physics of kinetic collisions more generally, and some work on our with VSim to model RF-driven capacitively coupled plasma discharges as well. And just generally speaking, these all fall under the umbrella of the VSim PD, VSim for Plasma Discharges package. And that's kind of where I come at this from. So Townsend discharges, this is kind of basic stuff, but that's where I'll start. Now this Townsend discharge happens with, we have a parallel plate geometry. We fill in between the plates, we fill the space with the neutral gas, and then we impose a fixed electric field between the plates. We've essentially set a constant potential difference between those two plates. And we pose the question, can this gas carry electric current? And if so, is it interesting? So you can imagine if you were to, before I do anything dramatic here, if we were to just let an electron go from the cathode, it would run up the electric field and hit the anode, and we'd have a current. Real life is a little more complicated than that, of course, and so as we emit an electron from the cathode, it will accelerate, and if it gets sufficiently energized, we'll hit a neutral atom and ionize it, and then we have 2 electrons and an ion, which means that pretty quick we have 4 electrons and more ions and so on. We get an avalanche, essentially. Every ionization event produces a new pair, electron-ion pair, and the electrons do just what the old one was doing. They keep running up the field to the anode. And the ions accelerate downward toward the cathode, although much less responsively because they're heavier and thus less mobile. When they get to the cathode, they hit it, and maybe they produce secondary electrons, which starts the cycle all over again. And essentially what we get is an amplification of this, whatever initial current we put out. There's some amplification having to do with the production of plasma through ionization. And so you also have other collisional processes that will affect the discharge physics. I'll talk about those on the next slide. There's an underlying assumption here that we never get quite enough charge to modify the electric field, so that's just imposed and such. And sometimes we forget about the secondary emission as well and just concentrate on the ionization process itself. But Townsend summed this all up in this equation here, which is the ratio of current that you actually get to the current you started with is some complicated function of the ionization mean free path x naught, and then these Townsend coefficients alpha and gamma, which have to do respectively with how many ionization events we make per unit length and how many electrons do we make when we hit the cathode. So we can look at this in VSim. I'm going to first talk briefly about collisions. What do the other collisions in this discharge do? Do we have, along with ionization, we might have excitation collisions where an electron comes and kicks one of the electrons in a neutral atom up to a higher state, but doesn't dislodge it all the way. This is essentially a sink of energy and momentum. And we expect that to reduce the overall ionization because we're taking energy out of the electrons before they get fast enough to be ionizing. We might also have elastic collisions, either of electrons or ions with the neutral gas. And this essentially is a redirection or a diffusion of the momentum. And you can think of this, in elastic collision, we don't lose energy, but we kind of redistribute the momentum into other components perpendicular to the field. So we're able to get to a higher particle energy overall. And we expect that to, depending on the cross-section energy dependence, that may increase or that may reduce the ionization, depending where we are on these curves over here. These are cross-section curves for various reactions we might see in helium, elastic, or excitation, ionization collisions and such. Then for the ions, we have charge exchange, backscattering type processes, and this again is a sink of energy and momentum. And instead of affecting the ionization directly, that may affect the secondary electron emission. If we go to a higher energy or lower energy state, do we get fewer electrons when we hit the cathode, or do we get more of them? So there's some dependence there. In VSim, there's a bit of technical issue, a bit of a technical issue in that how do we measure currents? Well, we have these particle histories that you probably know about if you're a VSim user, but what current do we expect? Now here, if we have an electron running up the field and hitting the anode, we'll call that 1 unit of downward current, if you will, because of the sign of the electron being negative, we'll flip the direction. We have an ion that hits the cathode, we'll also call that a unit of downward current, and so that's another +1. So essentially, if I kick off some number of electrons from the cathode, I expect to get at least that many at the anode. But in addition to that, I expect 2 more current units for every ionization event. And we make a pair, and then the electron comes up here as well, and the ion comes down. So that's +2. And then to get even more complicated, if I have an ion comes down, hit the cathode, and kicks off some number of electrons, as they come off, they leave behind that equivalent number of ions. And so I have M+1 ions coming in, and then I have M free electrons that are going to run up the field later. So the bookkeeping gets a little bit complex. And you can tell that by my font size here, that if I'm going to do the complex case, I put it really small at the bottom. And in the simpler case that our example covers at the moment, we're just going to neglect secondary emission entirely. We'll cross off this denominator essentially and try and compute this alpha coefficient using VSim. Essentially what we'll do then is we will spit out some number of electrons from the cathode, and then we'll catch them at the anode and count how many actually got there. Generally speaking, we'll catch more than we spit out, and that will have to do with the ionization. And So the difference of those two numbers is the number of ionization events that occurred. And we double that to get the total current. So this is the ionization current, 2m minus n. This is the initial current n. We add them together and divide by the unamplified current to get this ratio on the left of our equation. And it simplifies a bit, of course. I was going to mention to count particles, we can just do particle history, which uses this menu in the visual setup. And then whatever result you get, you can just multiply by dt over q, and that will give you a particle count. Experimentally, if you were to go and compute the Townsend coefficients, you would do something like was done in this paper in 1964. You fix the electric field essentially, and then change the voltage and the plate separation concurrently so as to maintain that fixed electric field. And then you just do a scan in voltage, and then you look at the current that you get for various values of the pressure and of the field. Yeah. So you can imagine this would be a perfect thing to be able to replicate in simulation, because we can just run a simulation, run another one, run another one, run another one. Nobody wants to do that manually. And so we have developed our new scan feature, which we hope you will find useful. When I've set this example up in the visual setup under the constants menu, I've set this voltage difference. And then I've set up the input file so that, you know, as we vary that voltage difference, we also vary the distance between the plates automatically so that we maintain a fixed electric field. So that distance comes in under the parameters. It's functionally dependent on this voltage difference, whatever I've set that to be. So that's all standard setup stuff that you're probably familiar with if you're a VSim user. What's new is under our design tab, which comes in on the left under the run tab, we can then take this voltage difference parameter, we can select it as a parameter over which we're going to scan, and we can list the values that we want it to take in that scan. Here I've listed 7 values, and so I'm going to essentially do 7 runs on this plot. And with one single click, VSim will set up those different runs in a subdirectory. It will do all the pre-processing, which is dictated in this column or these columns, and then it will sequentially or in parallel, depending on your system. You can choose that down here. It will run all of the simulations that you've asked it to in the scan. We have also, for this particular Townsend case, built an analyzer that will look over all of the output from the scan. So this is the scan analyzer Townsend.py, which will show up in your list of analyzers in the tab. And so we can tell it our scan name, our electric field, how many runs were in the scan and what we were scanning over and such. And then we can go in and compute from that, from the aggregated scan data, we can compute the Townsend coefficient. Essentially what we're doing is we're fitting an exponential to this curve and seeing what parameter best characterizes that exponential growth. And when we do that, we get quite good agreement with the data that's presented in this 1964 paper. The alpha being the Townsend coefficient divided by P naught, the pressure, comes in at 1.3, just as is predicted in the paper. So if you end up using this scan feature, and obviously you probably won't be doing this problem, but if there are use cases that are of interest to you, that you'd like an analyzer for a scan that does this thing or does that thing, that would be a thing we'd be interested in discussing. We'd like to make this scan feature and the associated analyzers more useful. So do reach out to us if that seems like a relevant thing that we can help you with. Going to change direction slightly. I'm going to talk about Townsend, Paschen curves now. And this is essentially a curve that tells you where these breakdown thresholds for Townsend discharges happen. Now, you can imagine if I had a very weak voltage and I sent an electron from the cathode to the anode, then nothing would happen, and we would not call that a plasma. But if I had a very strong voltage, you can imagine this avalanching, and there would be a breakdown and things would be more interesting. These Paschen curves, what they do is they tell you where that interesting physics is going to start, setting a threshold for where the breakdown will occur. So it's the same flavor of simulation. We have a parallel plate geometry, we have a separation distance, and we have a neutral gas filling the gap between the plates. And here we're going to vary the electric field strength and then compute the associated voltage that goes with that. What is found by Paschen is that the breakdown voltage depends on the product of the pressure and the plate separation, so P times D. And we want to figure out using VSim where this breakdown threshold occurs. Now this is clearly of interest. You can think of many situations where you would not want a avalanche breakdown type thing. If you have a grain elevator or something, that's bad. The spark sets everything on fire. And the physics of this discharge is, and of this curve shape, if P times D is too low, then essentially we have a small simulation. And if you have a small simulation and a large ionization mean free path, you don't get any ionization. Particles leave before they can do anything interesting. So unless you crank the voltage really high, you don't get a breakdown. Going over to the other side, if P times D is very high, that means high pressure, lots of background gas, your non-ionization mean free path is very short, and your electrons keep bumping into things before they can get up to the ionization energy unless you kick the voltage very high again. So it's high on the right, it's high on the left, and in the middle it comes down and hits a minimum that's dependent on the gas properties. And it turns out it's also slightly dependent on the material surface. You can have secondary emission coming off of your plates, and depending what the plates are made of, that will affect the shape of this curve. So here's the Paschen curve, essentially. This is from a paper by Phelps, and he's computing these curves for argon, but for lots of different metallic surfaces of the plates. Are they clean? Are they dirty? And so on and so forth. And you can see there's a fair bit of variation in the data depending on what your plates are made of and so on. Likewise, if you look at secondary electron yields, depending on the energy at which an electron hits the plate or an ion hits the plate, you may change the probability of emitting an electron out. And that's kind of encapsulated in these plots here. And these are plots that we have fit to piecewise linear functions and then pulled into VSim to do our study of Paschen curves. That study is covered in this paper, which was published last year. This is Joe Tice, who's a graduate student up the hill at CU. And we were able to use VSim to look at argon Paschen curves, and we were able to successfully compute those curves and get good agreement with experimental data. So these discharges have lots of collisions, elastic, and multiple excitation processes. We get ionization, and then, as I said, we've got energy-dependent secondary electron emission when the ions hit the cathode. From the title, you might deduce that we're also doing something clever with our particle simulation. We have a new method called speed-limited particle in cell, which is a feature we're developing in VSim, and we've put some of the basic functionality in VSim 12. It's not extensive at this point. We do not want to give you too much rope so that you can hang yourself with, as it were, but we want to put the basic functionality in and have people who are interested test it out. See if it's relevant to your discharges. Just give you a one slide summary of what speed limited pick is. Essentially, if you have a discharge where the ion physics is interesting and where you need kinetic electrons, that becomes problematic because your electrons are particles and they limit your time step because you have to resolve the electron motion, the plasma oscillations and such. And very often that physics is not interesting to you. You just care about what the slow ion distribution is doing if you run it for 100 microseconds or something. And you don't want to resolve electron dynamics on those time scales. So in SLPEC, what we do is we slow down those electrons. We make a rule that says they cannot exceed a certain speed. And we put on a threshold, a speed limit. We choose that threshold so that the only important electrons are the ones that are moving slower than that. Those will just follow conventional pick dynamics. And then the ones that are faster than that will just do whatever they do. And hopefully it's not very interesting. And because we have slowed down the fastest electrons, we are able to take larger time steps and we're able to get much faster run times. Order tens to hundreds of times faster than we would get from conventional pick. There are caveats here. You say 10 to 100 times faster and everybody wants to do it right away. But this is best for unmagnetized electrostatic plasmas where you care about the ion physics primarily, but where you have kinetic electrons in order to capture some kinetic physics that you want, maybe a non-equilibrium electron distribution or absorption or something. The work group up at CU is working to generalize the applicability of speed limited pick, and we will see more publications on that as that work goes forward. But for the moment, this is what it's good for. And I've got a couple references here you can look at, and I'd be happy to take questions about it offline or in the future if this feels like a thing you'd want. But going back to Paschen curves, these simulations where we decide did the plasma break down or not have to be run for a long time. Now, if you're above the breakdown threshold by a lot, and then you run the plasma, you run the discharge, and you start with 1,000 particles, and pretty quick you have 10,000, and sure, you got breakdown. If you're below the breakdown threshold, you start with 1,000 particles, and pretty quick you have 0, and yeah, you definitely did not break down. And if you're right on the border, you're going to have to run a long time before you know if you're getting gradually more, or gradually less, And so these simulations are very demanding computationally. You know, clearly the mass ratio of electron to argon is going to be problematic for your dynamics if you're trying to look at the argon physics. So we use speed limited pick to bring that ratio down a bit. And this is the result. In green, we have experimental data from Phelps. There's the paper I showed earlier. And then in red, we have standard pick in VSim. And then in blue, we have speed limited pick. The agreement's quite good, especially at high PD. Should point out that these simulations out here are definitely not ones you'd want to do with conventional pick because they would take you of order weeks to months. With the speed limit, we can speed that up by factors of tens or hundreds, and that makes things a good deal easier. Down here at the lower values of PD, we can simulate with both pick and SLPEC, and we get good agreement between the methods. We don't get quite as good of agreement with the experimental data, but you can see there's quite a bit of variation in that as well, and having to do with the metallic surface composition and such. But we feel pretty good about this, and it's a good demonstration of our new algorithm as well. From there, I wanted to mention, some of you have probably seen me talk about this before, we can also model RF discharges with the VSim PD package. This movie that I'll show you is a discharge posed by Miles Turner. And this essentially is a simulation benchmark suite that he's proposed in this paper. And pause the movie here for a second. What you see here, this plot is kind of busy, but I've got a mean density of electrons in red, ions in blue in this discharge. This is a one-dimensional discharge, and so I essentially two capacitor plates with a plasma in between, and I'm going to drive that plasma with RF on one of the plates. So I get current on the left, I get current on the right from the two species. You can see the potential down in the bottom here, and then the profile of ions in blue and electrons in red. And then this is the phase space, which I've done some rescaling on to make everything visible. Now you can see in the phase space, the electrons kind of slosh back and forth. They move left and they move right. And as they move to the right, or as they move to the left here, you can see there's a big electron current spike when they hit the wall. Then they're going to go right and we'll get a big electron current spike on the right. You can see that the electron discharge density kind of flops back and forth in the red here. Well, the ion density is pretty steady since the ions are not quite as responsive to the RF field. And you can also see these filamentary structures coming in. As the electrons retreat, we have this sheath that forms, and so we do a bunch of ionization where the electrons are. We create a bunch of ions, then the electrons move away and those ions fall down the sheath. And you can see the filaments coming down the sheath and coming down the other sheath on the other side. And you might envision catching these particles with an absorber and looking at their incident energy and what is the ratio of V normal to V perp, and what is the energy distribution and such. And you can do all kinds of interesting looks at the distribution in that way. Where'd my slideshow button go? Okay. So in this discharge, we have multiple flavors of collision, same as we had in the earlier Paschen discharges in Townsend. And what these discharges are really designed for is model benchmarking. The solutions that you get in steady state are very sensitive to the details of these collision processes and whether you're getting all the little bits of physics right that comprise those processes. So it makes for a very nice test suite. We've employed for nearly a decade now. We've had quite good agreement with each of the benchmarks. And by quite good, I've illustrated that over here on the right. This blue curve is Turner's prediction for the density, and then on the red is what we're getting, which looks pretty nice to me. Down below, I've plotted the time averaged electron energy distribution function for a couple of the cases. Now, Turner's data is in the triangles, and then VSim data is in the colored dots, green and cyan. And the agreement's quite good. Statistically, to match Turner's benchmark, there's some extra work that needs to be done. Some of the assumptions made by Turner are not quite physical. For example, the partitioning of energy in an ionization collision, how much energy goes to the ion, how much energy goes to the two electrons, how's that distributed and such. VSim has quite a complicated model for that coming out of the plasma literature. And for Turner, it's essentially a very crude division of labor, if you will, and we would need to write a brand new collision process and then run with that. And the only physics in that collision process is that it matches Turner's way of doing things and allows us to meet the benchmark in a statistically rigorous way. So we're doing that, but that will probably not be consequential for your problem. But we do plan in VSim 12.1 to put out some more details on that work and to verify that we are indeed rigorously matching these benchmarks and capturing the physics of low temperature discharges in the way that one might wish for. So generally speaking, we have been working with our VSim PD package. We feel good about our efforts to model physics that matches experiments. We got good agreement with Townsend discharges, good agreement with Paschen curves. We're doing good work in developing good analyzers for modeling RF-driven low temperature discharges, capacitively coupled plasmas. And then, as will be talked about in a talk tomorrow by Daniel Main, we're developing our capability for magnetron sputtering that brings in many of these features as well. Together with that, we've got a new parameter scan feature, which we hope will find you that you will find useful. And if you have suggestions for how we can make that better, we will try to pay good attention to those. And we continue to develop good particle and cell algorithms as well to give faster performance and simulation speed up and to capture the physics of your problem in a way that's computationally tenable. So it's basically all I've got. I'm going to put these slides up on my website, which I've linked here, if you'd like to download them, and if you'd like to reach out and talk about speed limited PIC or about any of these other discharges, be happy to do that later, but I'll also take questions now. So, thank you.
Well, thank you so much, Tom, for your presentation. So it looks like we have two questions that have been submitted from the audience. The first question is, how does the Paschen model change when the ionization rate coefficient depends upon E over N?
Well, that would just be, I think, a different scan, right? You could envision doing one scan for particular E over N, and then you would need to do another one for a different value. And I guess that's kind of captured here, right? In this plot from the 1964 paper, they're changing E, and so you get a different value. You would need to do a different scan to capture that physics, but it's essentially taking our 2D Paschen curve and projecting it into a third dimension as you vary that parameter.
Okay. Did the simulations include metastable states for argon?
Let's see. Don't actually remember that. For the Paschen, I don't think so. That's certainly a thing you could add. And then you would, of course, need to add all the collision processes associated with the metastable states, and the cross sections are different. And you could certainly do a more detailed look at that and what physics that brought in, and all the capability to do that is in VSim already. So you just need the cross sections and putting in all the reactions that you wanted. So that could certainly be done.
Very good. If anyone has any questions, there is a Q&A box on the bottom of your screen, and you can type it in there while we still have Tom available. We do have another day of TWSS tomorrow. We've got 3 different presentations. We have an introductory presentation that's at 9 a.m. And that is actually more for if you've never worked with VSim and you are just interested in a general overview and you want more general information than all of the detail we are presenting here. So that one will be at 9 a.m. Mountain Time. After that, then we have magnetron sputtering by Dr. Daniel Main, this is the new example that we have in VSim 12 that we are very excited about, because it's something that we are getting a lot of requests for, and we know that it's an important simulation to be able to do. And then we will have one more from Dr. David Smith to finish out the event. So any other questions before we end? We also released VSim 12 this week, or are releasing it. I guess I should say it should be available possibly by today, possibly by tomorrow. And we will get that out so that everyone can try some of these new features that we have been discussing as well. All right. That might be it, Tom, for today. So I really appreciate you taking the time to go through all of this with us. I know you were heavily involved in the development of VSim 12 as well. It's good to kind of see what that has led to here. Oh, we got another question. Can RF inductively coupled plasma be simulated?
I have not done that. I know inductive is more complicated than capacitive in terms of the plasma production sense. I would be happy to talk more about that offline, or we could get in a conference call with one of the AEs on that. But it would, I think, depend on the kind of problem you're trying to do. And yeah, that's the short answer. We need to look at what you're trying to do and the degree to which we have all the tools in place for you to do it. I think there would be a timescale issue that would be relevant. And
Sure.
so,
Sure. And you can send sales@txcorp.com is kind of our general email. So if there's something specific that you've seen today and you really want to get more information on that, you can certainly send us an email that way, and we can get some answers for you on that. So any final questions before we break for the day? Tonight, we are doing an encore presentation of the one that we did this morning with Dr. Andy Yu. So if you were not able to see that one and you want to see it live, once we have finished the event, we are going to have videos of all of our presentations. They will be on the TechX YouTube page. We will also have the presentations eventually will be uploaded to the TechX website as well. So we can try to get this information out to you. It looks like, okay, I think that is it right now. Okay, great. All right, guys, I think that is it. I look forward to seeing you all tonight, possibly, or certainly by tomorrow. Thanks so much. Thank you, Tom.
thank you.